Today, guys, we'll be going over LayerZero Read. It's a new data primitive that LayerZero has built for reading omni-chain state. A little bit of background, my name's Matt. I'm a developer ecosystem lead at LayerZero Labs. You can follow me at Uncrackable on X or Twitter. In the meantime, if you haven't heard of LayerZero to date has done over 135 million mainnet messages. We support 94 different mainnet blockchains, have totaled around 55,000 application contracts built on the protocol, and account for around 70% of all cross-chain value transfer. Why do so many apps use LayerZero? Well, LayerZero is a global ledger for permissionless, censorship-resistant, immutable bridge infrastructure. At a high level, LayerZero is an immutable interoperability protocol that enables any application to send tokens, NFTs, KYC, authentication, any type of data that you can imagine on-chain from a source blockchain to a destination blockchain, giving you, the application developer, tools to configure the type of security that you use to route these messages and the type of execution that you need to deliver these messages once they are verified and reach the destination chain. At a high level, though, let's zoom out a little bit from this perspective. Bridges in general are focused about one main thing: connecting isolated groups of people, and more importantly, the information that they hold. Using this information, we can coordinate the exchange of goods and services, and via that exchange of goods and service, we can coordinate broader, more financial use cases around that asset transfer. This is no different for blockchains. Blockchains each have their own realities about each isolated network. Some are better for speed, cost, security, community, different types of app use cases, etc. And we see this becoming more prevalent in the way that developers build on-chain. More and more developers are moving to a cross-chain environment. But one of the realities of cross-chain development is that it's not like a single blockchain only. When we look at a simple chain itself, like Linea, for example, in ERC20, an asset transfer from one user to another simply involves an atomic transaction executed once that debits users from one account in the form of a mapping and credits those tokens to another user. As soon as you move to more than one blockchain environment, this immediately becomes more complicated. Suddenly, I have to figure out, how do I ensure state gets executed on a source blockchain and then relay that state change over to the destination to credit or target some amount of state change as a reaction to the initial transaction I made, all without getting rugged or destroyed in the middle of it. It's a very difficult problem and has led to millions of dollars of losses in this space. Historically, the way that we solve this problem is with a concept of monolithic bridge security. The idea that one centralized party in the middle, whether that's literally just a central party going in routing orders cross-chain, where that's a collection of permissioned validators, or a middle chain in the middle between these two blockchains, routing messages, determining how they are valid, and then executing them on destination. Regardless of the security that you choose, the main problem that we have to think about is what happens when that security fails. Well, not just your application, but every application using that validator set is now affected. And historically, this is the reason why monolithic bridge security exploits account for 4 of the 5 largest hacks in the blockchain space. And if we look at the developer trade-off that we're faced in bridging, you're now forced to pick, essentially, as an app developer, between 2 points on the security cost curve. Either inherit weak security guarantees that have low cost for your average user, or high average cost for a gained amount of security. Obviously, reality isn't as linear as this, but I think it paints the picture nicely that you as an app developer are now forced to pick between 2 realities for your security when you use bridges on any blockchain network. Beyond that, LayerZero was built to basically solve this problem of forced selection of bridge security. At a high level, LayerZero is comprised of an omni-chain messaging solution where any application can interact with a LayerZero endpoint and configure the type of security that you want to use to relay messages from chain A to chain B, both in terms of the type of security you use, the number of validators in the set, and also what the threshold of security is for that validation. On top of the actual messaging, we run executors that anyone can either establish themselves on an app use case or opt into to deliver gas automatically for the user on the destination chain once a message is verified. And finally, the most important part for hackers, smart contract application standards that enable you to easily build cross-chain applications like OAP for moving any raw data between chains, Omni-chain fungible token, or OFT, for ERC20 transfers between chains, and the omni-chain non-fungible token for ERC721. What this gives you as a combined set is the ability to not have to choose between point A or B on this cost curve, but instead choose any of the points in between that fits your application's use case, and as new validation techniques come online, permissionlessly update that validator set depending on what your application needs, or lock it in depending on your access controls within the application itself. Beyond the security, the other benefit you get from using LayerZero is this ability to gas drop from a source transaction. The ability to, after a message is verified, be able to execute it automatically for the user on their behalf on the destination, all while giving them the destination gas token that they need, either directly in the call you're executing on destination or just dropping it directly to an end user's address. So zooming out a little bit, I told you a lot about what LayerZero is, but not a lot about the topic of this workshop. How do I actually read omni-chain data and state? Let's dive in a little bit deeper and understand what the protocol is actually doing under the hood to enable this. At a high level, the way that LayerZero works is that an application will construct a send message by calling the endpoint send method. This message can be comprised of bytes and can hold any type of data that you want as an application. You'll provide this message a destination chain identifier, also known as an endpoint ID, and then a configuration about what DVNs, decentralized verifier networks, and executor you want to use. From there, the DVNs will go and verify that message using each their own verification schema internally and deliver that verification to the destination chain. On-chain, your application is enforcing that this verification is valid based on the parameters that you've set in this library configuration. From there, an executor can automatically deliver this message to the actual method endpoint.lzreceive, which gets routed through to your internal application's version of that call. What this enables is you to basically control the send process, validation, and then execution of your message. That at a high level is what we're doing. One of the popular ways that you would bring data back from a destination network to your source chain is using a concept of this ABA message pattern. What an ABA pattern basically is doing is saying within the receive call, execute another send call back to the sending chain. So from this model here, we had chain A sends a message, it gets verified and delivered on the destination, and within the destination call, execute a return call back. Some of the obvious problems with this design pattern are that, one, you're paying for fees on both sides, two, you're waiting for execution to finalize on both chains, and three, you're ultimately just trusting the same internal party for both these transactions. And so at LayerZero Labs, we thought, well, what if we could streamline this process and make it easier for you to actually receive the target data that you want on a destination chain, all without duplicating the transaction cost? That's why we built LayerZero Read. LayerZero Read at a high level is the ability for you to basically have that same workflow, define an origin chain that you're deployed on, select some target data chains to read from, and then using your security stack and the executors, fetch that data from the target data chain and then bring it back to the source that you want to send from. The way that it works is exactly the same as normal protocol spec. An application still creates a send message via the endpoint contract. It's the same endpoint contract that you use for normal cross-chain messaging. The only difference is that now we have a read message library that basically constructs the correct message to emit out to your DVNs, and the DVNs are all running a node to fetch specific state from each of these blockchain networks. At a closer look, the only difference in terms of messaging is that an omni-chain message delivers the same message from the source chain onto the destination. An omni-chain read generates a request that you submit off-chain, and then that request gets a response that returns back on-chain. And what's really cool about this is that it changes the normal protocol spec from this cross-chain message delivery service to this ability for your DVNs to go and look at a target contract at a specific block number or timestamp, wait a specific number of confirmations that you set, and then access any call data from that target contract. The second cool thing is that after you actually generate these requests, you can then create compute logic. So using functions that I've defined in my application, LZMap and LZReduce, I can then manipulate the data that's being requested and return something completely different back to my verification, ultimately to have it executed back to my contract. So what this ultimately builds to is this ability to essentially initiate a request from any chain and bring specific state back on chain that you want. The example that we'll be going through today is actually fetching live Uniswap ETH to USD pairs from multiple different blockchains, aggregating that price off chain using our DVNs, and then bringing it back on chain as a request. For this workshop, if you go ahead and scan this QR code, it'll give you a Linktree link. This Linktree will have links to the example code that I'm using, to the relevant documentation about LayerZero Read, and then also just more information about LayerZero in general. Cool. We're going to jump into the code example, and I'm going to show you exactly how to get started. I have two windows pulled up here, one that I've already deployed, and then one that we can base our contract off of. The first thing that we're going to do is go ahead and use LayerZero CLI tool to get started. The simplest way to do this is running LZ enable read example equals 1 in your environment, and then this command npx package, create LZ OAuth at latest. What this command will do is basically create a prompt for you to build a new repo. In this case, I've already created one, but I'm going to call this myRead2. It'll give you a list of contracts that you can start from. There's OFT, OAP, ONFT, some upgradable variants if you want. In this case, I'll do OAP read. This is the one that has all of the read contracts installed. Pull all the dependencies down that I want to use, et cetera, et cetera. In the meantime, what's happening in this contract is that OAP read is just a simple example contract based on this standard, OAP read here. OAP read you can find once these dependencies get pulled in node modules, but in the meantime, I actually have them pulled up for us here already. We can go ahead and bring this contract up. I'll actually walk you through live really quick how this Uniswap v3 quote demo works. So at a high level, I'm going to pull terminal down really quick and just get all this stuff sorted. Perfect. The Uniswap v3 quote demo is just an extension of OAP read. OAP read itself is just an extension of OAP, the base cross-chain messaging contract. The only difference that we're actually doing is setting up one function, a read channel. The way that read works is that you can define specific messaging channels that you want to send to, and then use them for constructing your data requests and compute logic. In this case, looking at this contract, I've defined a couple main constants. First, just a chain config with the Uniswap v3 quoter address for the target chain that I'm looking for, the token in address for wrapped ETH, the token out for USDC, and then also just defining these constants here directly in the contract. You can see here that each chain has an endpoint identifier that I'm using. In the constructor of this contract, I'm setting up the LayerZero read channel. The channel ID is just an arbitrary identifier for where I'm going to be sending to and how I'm going to be reading from. And then for each of these chain configs, again, just pulling all of the relevant Uniswap v3 pool contracts for iQuoter v2 and setting them up here. The way that this read average Uniswap price function works is that we're essentially generating a read command and then passing it to the normal LayerZero send method that you would use. The only difference being we're passing the read channel as the endpoint ID and a command as opposed to our LayerZero message. Under the hood, the way that get command works is that it is a standard function that you want to set up within your application. This get command will basically define the number of call requests that you want to have executed cross-chain. In this case, I'm just using the number of pairs that I've been putting, 3. And I will define basically as call data the type of params that I want to essentially use as call data on these target networks. Here I'm using the iQuoter v2 from Uniswap v3, quote exact input single params. I'm encoding this as call data for this function selector, and then generating in this for loop the number of read requests for each of the chains that I want to read from. Under the hood, the second thing that I'm doing is defining a compute request. The compute request is basically how am I aggregating all of this data once it's returned. There are a couple compute settings. If I do, for example, compute setting 0, this is LZ map. If I do 1, this is LZ reduce. Let me just fix that, not LZ meow. And then 2 is LZ map and reduce. Again, you can look for these function methods wherever you like. In this case, we're looking back on the same chain at this address. The function LZ map is basically deconstructing for each response what is the actual output. So in this case, we're getting the response from the Uniswap contract of 4 main return types. The only one that we care about is the actual amount out that's being returned. And then LZ reduce is defining, once we have all of these aggregated responses, you can see here we're getting a bytes array of call data for responses. We're taking all the responses that we get from each of these chains, aggregating them, and then just doing a simple average to basically get the average amount out from each of these networks. And then finally, the only thing that I'm getting back in LZ receive is what is produced from the ABI encoded argument here in LZ reduce, delivered to my contract on chain. So high level, walking through this again, we construct in the send call a command. That command is comprised of both the requests for data that we want to go get on different target networks, the call data for those chains, and the actual address that we're quoting from, and then some compute settings. In this case, looking back on the source chain for LZ map and LZ reduce to go and aggregate this function logic. And what's cool is that these functions will get executed off-chain bar DVNs that we've configured, and then only this final ABI encode from LZ reduce will be delivered as a message to LZ receive. So a lot I kind of went over there. Let's actually look at this kind of in action a bit more. We're going to zoom out here. I'm going to pop into Arbitrum. First, I'm going to query this quote price for the transaction I'm going to do, in this case in Way. What I'm going to do from here too is then grab this Way price, go to Ether converter just to simplify this process a bit, punch in the conversion to Ether, then go to write contract, read average Uniswap price, throw the amount in, don't have any extra options that I want to add. We'll write on the block explorer this call, hit confirm, and what will happen here is it'll generate this transaction on Arbitrum for us that got confirmed basically instantly, and then we can go into LayerZero Scan and actually see what's happening under the hood here. Inside LayerZero Scan, this basically just serves as a record of all transactions processed by the protocol. It might take a second for it to index and come through. Here we go. You can see that we have a request transaction hash from Arbitrum, and we're waiting for the response transaction to land. You can see here that we have a request payload that we generated. There are some decoding instructions that you can follow from the documentation about how to decode any incorrectly constructed calls that are made here. But what will basically be outputted back on chain while we're waiting for this one to land is the aggregated price from all of these different networks that we're reading from. One of the things that I've done here as a transaction already is reading the average price earlier, I think 2 or 3 days ago. We can basically see here that we're getting executor fee paid, DVN fee paid on the send side and the packet sent event. And then from the overview section here, if we go and add this transaction to Tenderly, this one's already been indexed. We can see the destination here. Open it up, go to our logs, and we can see the aggregated price for ETH a few days ago was 3307, looking directly from all of the Uniswap pools that we have configured. So what this basically enables you to do is take data in the form of a call data request that we saw here, aggregate from that call data request the responses and return values that we get on chain from any type of view or pure function or public state variable that's on a destination blockchain, and then use the LZ reduce and LZ map methods to basically take all those requests that we want, aggregate them down to one final response payload, and then deliver that response payload to LZ receive. So yeah, I hope this gave you kind of a good overview of how LayerZero Read works. Now open any questions you guys might have about the protocol, about cross-chain messaging, read messaging, things like that.